Okay, good afternoon, all of you. Welcome to this 40th lecture of refrigeration air conditioning. So before the lecture, I would like to remind you. So already I have put a notice of Diwali holidays. So it will be from 13 to 17. From 18 onwards, on 18 there will be I think lectures, and on 19 onwards your ISC will be there. So on ISC will be like a 19, 20, and 21st. Our RAC paper will be for last paper is there on 21st November. Okay. So the format will be like previous what we did 2 to 3 months back. So you have to write that paper, you have to scan it, and you have to send that PDF to me. Okay. So for all the subjects, this format will be there. There will be a time slot. Question paper will be sent to you by mail and WhatsApp also. Then you have to write it on some paper. You have to scan it, and you have to send that PDF to me or the whoever the subject teacher is. Okay. So that notice also I have put on our group. So please check that. So Diwali holidays 13 to 17, and ISC 1 will start from 19. Okay. So for ISC, uh, I have to cover our first 3 COs, course outcomes. So in that case, I will try to cover first section and a little bit of second section also. Right. So 3 COs will be covered. Okay. So we'll start today's lecture. So we'll start with the previous revision. So in previous lecture, we have seen some of the processes. So I have taken revision already on this. So all the processes involved in psychrometric chart are shown on this diagram. So cooling and sensible heating, sensible cooling, humidification, dehumidification, and all the mixed processes like heating and humidification, cooling and dehumidification, that are all shown on this diagram. Okay, so this is for your reference only, and it depends on the numerical what you are facing, what condition is involved. The special case I showed you, evaporative cooling. So this is what happens in air coolers. So minimum temperature from evaporative cooling you can get is its wet bulb temperature. Then these are the commercial products. First one is the steamer, and it is a classic example of humidification. You are adding moisture content, so that will be humidification. Second is dehumidifier. And third one is evaporative cooling, that is also very common to you. So these are some of the commercial products for the psychrometric processes. Another factor we have seen, sensible heat factor, and we have solved numerical also. So sensible heat factor is a ratio of sensible heat to the total heat. Okay, so there I explained one with the help of one psychrometric diagram here. Okay, so suppose you are at a point 1 and you go to the point 2. Okay, so this process from point 1 to 2, this process you can show with the help of a dash line like this. So there will be a vertical line, then there will be a horizontal line. So horizontal part is nothing but its sensible heat, and vertical part is its latent heat. Okay, so total heat we can write it as a sensible heat plus latent heat. Okay, so and sensible heat factor will be ratio of sensible heat to the total heat. Then we solved a numerical which was related to the cooling, and it was not only sensible cooling, it was cooling plus dehumidification. Okay, so air with some moisture content comes in contact with cooling coil. Cooling coil temperature is somewhat equivalent to its dew point temperature. So that means that whenever air will contact with the cooling coil, the moisture or the water content will be condensed on the coil. So there will be condensation of water, and then we can remove the water. So in short, cooling is happening, and as well as we are removing the moisture content. Okay. Then we have solved this numerical in last lecture. So what was asked is here, what will the final condition, what will the cooling capacity of the coil, and what will the sensible heat factor, right? Then similarly, there will be numerical which will be related to heating and dehumidification. Then there will be a numerical which will be related to heating and humidification. Okay. So there are some numericals related to this. So we'll solve these numericals, but in today's lecture we'll cover very important topic that is called as adiabatic mixing. Okay. So if you are taking notes, write down this title, adiabatic mixing. And I will show you first what is its real life application. Then we'll see what is its actual process. Okay. So suppose there is a room. This is a room, and this room is maintained. This room is maintained with the help of a air conditioner. Okay, so this is its AC part. Then there will be some grills here, and there will be a supply vein. Okay, outside part will be as usual condenser plus compressor. So this will be outlet part. There will be a supply line. There will be a return line. So in basically this room is maintained with the help of a air conditioning. Okay, so when you install the AC in a room, what is actually happening here? It is recirculating the air. So AC is taking the air inside. So this will be its entry. It will take the air inside. It will cool and also dehumidify the air. Then it will supply the cooled and dehumidified air to the room. So continuously it is removing the moisture from the air and also cooling it. Okay, so when I install a AC in a room, it is cooling as well as dehumidifying the air, but in this case air is being recirculated. So I am not adding a fresh air to the room. त्यामुळे कसं होतं, जसं एखादी रूम किंवा एखाद्या कारमध्ये आपण एसी लावतो, थोड्या वेळानं आपण कारची विंडो आपल्याला खाली करावी लागते. अदरवाइज व्हॉट विल हॅपन, सफोकेशन विल हॅपन because that carbon dioxide content in the room will increase and suffocation will start to happen. In that case we need some fresh air. So in case of ACs we are just recirculating the air. Okay, now when I go for a mall or if I go a commercial building, their case is different. So suppose this is an office hall, and for this office hall I need a AHU. ह्याला काय म्हणतात? AHU. So AHU means air handling unit. So what air handling unit does in this case, it takes a fresh air. So it will take a fresh air. This is a fresh air it will take. Then if this room is being maintained, so it has some false ceiling, what we call in general today is a POP. This is its false ceiling. Okay, in false ceiling diffuser are being installed. So this is supply diffuser, then there will be a return diffuser, there will be again another supply diffuser. Okay, so this let us say this is a supply diffuser, this is a return diffuser, this is again supply diffuser. Supply diffuser will supply the air, return will take the air. Okay, then there will be a duct from the return air, it will go to the AHU, air handling unit, like this. And in AHU what will happen, it will take the fresh air as well as it will take the return air and it will give the supply air. So supply air will be its outlet. So this is it, supply air. So it is taking the fresh air, taking the recirculated air, then it is supplying the air. Supply air, this will be connected to the supply diffusers. Okay, so this will be connected to the supply diffuser. Air will be supplied, some part of it will be recirculated. Okay, so this is our AHU. Then there is another equipment which is called as fresh air handling unit, which is also called as FAHU. Okay, FAHU. Its sole purpose is to take the fresh air. So it is not taking the recirculated air, it takes only fresh air and it gives the supply air. It gives the supply air. Okay, but in this adiabatic mixing we are not considering this, we are considering a AHU. So why we need a recirculated air? So suppose fresh air is coming at let us say 40 degrees Celsius. inside temperature we want to maintain at 25 degrees Celsius. So in this case, if I take some amount of recirculated air, which is at, let us say, 26 degrees Celsius, then the load on the AHU will decrease. So also the amount of fresh air, that will also decrease. So when I use some amount of recirculated air, the load on AHU decreases. So AHU does not have to work to its maximum limit. In that case, it can just use some part of recirculated air, so that load on AHU will decrease, and then we'll get a supply air at a, let us say, 22 degrees Celsius. Okay. Now you may ask that, sir, we have to supply the air at 25 degrees Celsius, then why the supply temperature is 22 degrees Celsius? So I am here considering all other factors. So there will be a heat transfer to this duct, right? There will be a heat transfer to this duct, that also I have to consider. So finally, when the air will enter the room, it will be again at some lower temperature, let us say 24 degrees Celsius. When it will come finally inside the room, there will be again heat transfer to the room, and then finally its temperature will be 25 degree Celsius. Okay. So always remember, if I wanted to maintain the room at 25 degrees Celsius, supply temperature should be a little bit lower. Okay. So this is the difference between the direct cooling system. These are also called a DX system, direct expansion or direct cooling system. And this is a centrally cooled or central, or another word, it is there, chilled water systems. Okay, so in DX system, what is happening? We are installing a AC in a room, but it is recirculating the air. It is not using any fresh air. But in case of AHU, AHU will take fresh air. It will take some amount of recirculated air. It will mix these two streams together, and then we'll get a supply air. Okay, this is the main difference between chilled water systems and direct expansion systems. Now coming to our point, adiabatic mixing. So if I draw a simpler diagram here of adiabatic mixing, so let us say there is a stream 1, then there is a stream 2, okay, then I get a outlet. So this is a stream 1 of air, this is stream 2 of air, this is a outlet. So this will come with some mass flow rate M1 with enthalpy H1 and specific humidity, sorry, this should be W1. It will come with some mass flow rate M2, H2 and W2. Okay. So here the mixing will take place, and finally I will get M3, H3 and W3. Okay. So in this case, it is assumed that all these walls are insulated. All these walls are insulated. That means there is a adiabatic mixing. Adiabatic means there is no heat transfer. So from this system, there is no heat transfer to its surrounding because the walls are insulated, right? So in this case, if I apply the law of conservation of mass, so applying law of conservation of mass to air, in that case, what will happen? It will be like M1 plus M2 will be equal to M3. Okay. Then if I apply law of conservation of energy, so these are all first law. This is also called as first law of thermodynamics. So applying law of conservation of energy. In that case, this will be like M1 H1 plus M2 H2 will be equal to M3 H3, right? Then if I again apply law of conservation of mass to only water, so applying law of conservation of mass to water. So in that case, I have to multiply the mass flow rate of air by its specific humidity. So it will be like M1 W1 plus M2 W2 will be equal to M3 W3. Okay. So let us name these equations as equation 1, equation 2, and equation 3. Right. Now what I will do, so I will put the equation of M3 like this, which one is M1 plus M2 into this equation. Okay, so putting value of M3 from 1 into 3. Okay, so what will happen here? M1 H1 plus M2 H2 will be equal to M1 plus M2 into H3. Okay, so I will simply do some adjustment here. So this will be again M1 H1 plus M2 H2 will be equal to M1 H3 plus M2 H3. So what I will do, I will take all the M1 terms on one side and M2 terms on the another side. So this will be M1 H1 minus M1 H3. So this will be equal to M2 H3 minus, sorry, this will be M2 H2. So I have taken all the M1 terms on LHS, M2 terms on RHS. So this will be M1 into H1 minus H3. This will be equal to M2 into H2, H3 minus H2. Okay. So I will take the ratio here. So M1 upon M2 will be equal to H3 minus H2 divided by H1 minus H3. Okay. So this is what I get here. This will be equation number 4. Okay. So a very basic simplification is here. I started with the law of conservation of mass to the air. So if you see the diagram, obviously M1 plus M2 will give you M3. If I apply law of conservation of energy, in this case, I have to multiply by, mass flow rate by its enthalpy. So M1 H1 plus M2 H2 will be equal to M3 H3. Okay, this is also correct. If I apply law of conservation of mass to water, so in that case, I have to multiply mass flow rate of air by its specific humidity. So I will get M1 W1 plus M2 W2 equal to M3 W3. So that will be my equation number 3. Now what I have done here, in this case, I have put this expression of M3 here. That is M1 plus M2 into this expression. And after simplification, I get this ratio. So M1 upon M2 will be equal to H3 minus H2 divided by H1 minus H3. Okay, so write it down. Okay, now similarly, okay, so wait, so this point is not covered yet. So similarly, if I go putting value of M3 from equation 1 into 3. Okay, so in previous equation, what I have done here, so here I have put the value of M3 into equation 2. So this should be here 2 into 2. Okay, so I have obtained this ratio. If I do similar case here, if I put the value of M3, that is M1 plus M2 into equation number 3. Here I have to replace this M3 by M1 plus M2. Okay, so I will replace this equation number 3, that value of M3. So this will be again M1 W1. So this is like applying law of conservation of mass to water vapors. M2 W2 will be equal to M1 M2 into W3. Now if I simplify this again, so I will get a similar result. So this will be W1 M2 W2 will be equal to, I will simplify this bracket. So this will be M1 W3 plus M2 W3. Now if I take all the M1 terms on LHS, M2 terms on RHS, so this will be M1 into W1 minus W3 will be equal to M2 into W3 minus W2. If I take a ratio, this will be M1 upon M2 will be equal to W3 minus W2 divided by W1 minus W3. Okay, so this is the equation number 5. So I have obtained here equation M1 upon M2 equal to H3 minus H2 divided by H1 minus H3. This is related to enthalpy. If I apply same for the specific humidity, I get this equation M1 upon M2 equal to W3 minus W2 divided by W1 minus W3. Okay. So what we are dealing here, I will revise. So I started this adiabatic mixing by showing an example of a room. In this room, I have used AC, but in AC, what happens? We are just recirculating the air. We are not adding any fresh air. Now, if I go a commercial building here, in commercial building, we are using AHU. AHU means air handling unit. It is taking in fresh air, then it is taking some recirculated air. It is mixing these two streams. Then we are getting a supply air. Okay, so fresh air plus return air, that will give you supply air. So if I apply law of conservation of mass here also, so I will get a similar equation. So fresh air plus return air, so that will give you supply air. The supply air will be supplied with the help of supply diffusers. Okay, so these are the supply diffusers, and some part of it will be recirculated. So these are the return diffuser. So return air will go to return duct. So we have fresh air duct, we have a return air duct. These are combined together at the AHU. AHU will mix it and it will get a supply air. Okay. If I show a simpler diagram for that, it will look like this. So we have one stream, then we have another stream here. It is mixed together here, then we get a third stream. Right? So if I apply a law of conservation of mass, it will be look like this. M1 plus M2 will be equal to M3. Same as previous, fresh air plus return air will be equal to supply air. Then if I apply a law of conservation of energy, this equation will get, if I apply law of conservation of mass to water, we'll get this equation. Then after simplifying all this equation, I will get this ratio. So in case of adiabatic mixing, so why we are calling this adiabatic mixing? So all these walls of these ducts here, these are insulated. So these are the insulated walls. So there will be no heat transfer to the surrounding. Okay. So this is the case of adiabatic mixing. So if I show similar process on psychrometric chart, so suppose there is a psychrometric chart. Okay, so you know on horizontal we have dry bulb temperature dBT. On vertical we have specific humidity. This curve is nothing but 100% RH. That means air is saturated. Okay, so we have one point here P1, and then we have point P2. These are the two streams. Then when these two streams will combine each other, then we'll get a point P3. Okay, so this is at mass product M1, H1, W1, then P2 is at what, M2, H2, W2. Then we'll get a final point, that is a M3, H3 and W3. Okay, this is the case of adiabatic mixing. A very interesting case here is fog formation. So whatever fog we see, so this is the season of fog formation. So I will show you what happens in fog. So again, I will draw a psychrometric diagram. So especially in winter season, when a steam, which is very hot and humid, so there is a condition P1. So P1 is a point which is hot and humid. So humidity is high and its temperature is very high. It comes in contact with another stream, which is a cold and humid. So this is a cold and humid. So when these two streams combine or are mixed together, we'll get a line like this. And our final point, that is a point P3, will lie on this point, will lie on this line. Okay. So as you see, point P3 is outside of the 100% RH curve. 100% RH curve means this air is saturated. Point P3 lies outside it. Okay, so that means here the air is saturated. That means there will be a dew formation. Okay, so whatever fog we see in winter season, सकाळ सकाळी आपल्याला जसं जे मोठं धुकं दिसायला चालू होतं. So in that case, what is happening? Any hot and humid air from the atmosphere, if it comes in contact with the cold and humid air which is nearer to the ground, in that case we'll see a fog. Okay, so this is the formation of fog. Point P3 is the fog condition. Okay, so this is outside of this saturation curve. In that case, water droplets will be observed on the substances. Right, so this is the phenomena of fog. Okay, so this is very special case of adiabatic mixing. In adiabatic mixing, we have two streams which combine together. So there is a stream 1, and then there is a stream 2, then finally we get a stream 3. Adiabatic mixing is called because all these walls of this mixing or these ducts are insulated, so there will be no heat transfer to surrounding. And this is how adiabatic mixing will look like. Point P1, point P2, there will be a straight line. On the straight line somewhere, this point P3 will lie. And there is a special condition for this, which is called as fog formation. So if a very hot and humid air comes in contact with cold air, in that case, this will be the line. And there will be a point P3, which will lie outside of our psychrometric chart. That means that it is saturated, as well as there is a condensation of water droplets. Okay, so we'll solve a numerical related to adiabatic mixing. So here is the numerical in front of you. So I will read it. So there is the air stream 800 meter cube per minute of recirculated air. So this is a return air at 22 degrees Celsius dry bulb temperature and 10 degrees Celsius dew point temperature is to be mixed with 300 meter cube per minute of fresh air at 30 degrees Celsius dry bulb temperature and 50% RH. Determine the enthalpy, specific volume, humidity ratio, and dew point temperature of the mixture. Okay. So numerically is very straightforward. There is a return air, there is a fresh air. These are two mixed together. Then we'll get a supply air. So we have to find out the condition of a supply air. Okay. So I will write it. So given data here, given fresh air, okay, fresh air, let us denote it as 1. So this will be TD1. It is 30 degrees Celsius. Then we have 5.1, which is 50%. Okay. We have return air or recirculated air. Let us denote that as a point P2. So in that case, TD2, here it is 22 degrees Celsius. And then we have a TW2, which is a 10 degree Celsius. Okay. Here the mass flow rate is also given. So in this case, M1 is 300 meter cube per minute. And here we have M2 as 800 meter cube per minute. Okay. Then we have to find out the condition of supply air. So supply air, let us denote it as a 0.3. So in that case, we have to find out its enthalpy, that is H3, specific volume, that is V3, humidity ratio, that is W3, and we have to find out its dew point temperature. Okay, so dew point temperature 3. Okay, So I'll show this process on a psychrometric diagram here. Okay, so this is a dry bulb temperature. This is a specific humidity. This is once again 100% RH curve. Okay. Now I'll roughly point show the point here 30 degrees Celsius. So let us assume this is 30 degrees Celsius. This is suppose here 22 degrees Celsius. Okay. So I have to find a point on dry bulb temperature line, that is a 30 degrees Celsius, and I have to find out a curve of relative humidity of 50% RH. So there is a curve, there will be curve of 50% RH. So this will be my point P1, or let us say 1. Okay. Now it undergoes some cooling in this case, and let us say this is our 22 degrees Celsius dBT point, and I will plot it here. Okay, then I have to look on this line, so there will be a scale of WBT, so there will be values of WBT here. Okay, like this, there will be lines of wet bulb temperature. So let us assume this is a point. Anyway, we are going to plot that point on psychrometric chart, but for understanding purpose, let us assume, let us first understand the process. So let us say this is a point 2, and then there will be this line of adiabatic mixing, and somewhere in between there will be our point 3. Okay, so we have to find out its dry bulb temperature, we have to find out its enthalpy. So there will be an enthalpy scale here. Okay, so that we have to find. And what else we have to find out? Humidity ratio. Humidity ratio means we have to find out its this value W3. Then we have to find out its dew point temperature. Dew point temperature, for that you have to take another horizontal line up to saturation curve. So this will be its dew point temperature 3. Okay, so I will repeat again. So we have a fresh air at point 1, which is at 30 degrees Celsius dBT, 50% RH. That point I have plotted. Then we have another point which is at 22 degrees Celsius dry bulb temperature and 10 degrees Celsius WBT. Okay, that point also I have plotted, point 1 and point 2. I have to join those 2 points and create a line. So on that line somewhere this point 3 will lie. Okay, so how to find out that the point? Let us see. Okay, so from the derivation of adiabatic mixing, I have this formula m1 upon m2 will be equal to h3. So let me just check what is the formula. H3 minus H2 minus divided by H1 minus H3. Okay, H3 minus H2 divided by H1 minus H3. Now in this case, this mass flow rates are not directly given, that I have to calculate. Okay, so mass flow rate 1 will be equal to volume flow rate divided by specific volume 1. Okay, and mass flow rate 2 will be equal to volume flow rate divided by specific volume. So this will I will obtain from the psychrometric chart. All this volumetric flow rate for point 1, it is given as 300 meter cube per minute divided by specific volume. Here it is given as 800. Okay, so be ready with your calculators. So there is a psychrometric chart provided by Ashray, which is in front of you. Okay. So So see here, our point 1 is 30 degrees Celsius dBT. So this is the line for 30 degrees Celsius. I will go vertical direction and I will stop at the 50% RH. So 50% RH, this is a 40% and this is a 50%. So this is a 50% RH curve. So this is my required point. So this is the point 1. Okay. Now next is point P2 is 22 degrees Celsius dry bulb temperature and 10 degrees Celsius wet bulb temperature. So 22. So here is 20. Okay. So 21, 22. So this will be for 22 here. Then I have to go in vertical direction for 22 and stop at 10 degrees Celsius WBT. So see here, these are the scale for WBT. So here it is 5. Here it is 10. Okay. So 10 degrees Celsius, there is a dash line, inclined dash line, which is coming like this. Then I have to stop it. It's there intersection. Okay. So 10 degrees Celsius, it will come up to here and it will intersect here. So this is my point 2. Okay. So this is how I obtained the points. Now I have to connect these 2 points with the help of a line. Okay, so assume that there is a line. So this is a line of adiabatic mixing. Somewhere on this line, my point 3 will lie. Correct? Now here I have to find out the enthalpy first. So at the point 1, my enthalpy, how to find out the enthalpy? I have to go from point 1, I have to go in inclined direction like this. So I will go up to the enthalpy scale. So here I will get a value of 60, 62, 64, 65. So enthalpy at point 1 is 65. Okay. Then I have to find out its specific humidity. So I have to go in horizontal direction like this. So I have to check for this value here. So here it is shown as 14, somewhat below than 14. So this will be 12, 12.5, 13, 13.5. So this humidity, specific humidity will be 13.5 grams per kg of dry air. Okay. Now similarly for point 2 also I have to find out its enthalpy. So I have to go in this direction. So here I will get an enthalpy of 30. So at point 2 enthalpy is 30 kilojoule per kg of dry air. If I want to find out its specific humidity, I have to go in horizontal direction like this. So I'll get a value here. So this value is 2, 2.5 and 3. So 3 grams per kg of dry air. Okay, so remember these values 65, 13.5 and 33. So here at point 1, I have enthalpy which is 65 kilojoule per kg and I have and at point 2 I have enthalpy as a 30 kilojoule per kg and specific humidity there it is 3 grams per kg. Okay, so what is remaining here? Specific volume, that will also I will follow from the psychrometric chart. So where was I? Okay, so once again I think I have to find out. Okay, so this was my point 30 and 50. So the point will be here. This is my point 1. Then 22 and 10. This will be my point 2 here. So at this point, 2 points, I have to find out its specific volume. So here it is straight away given 4.2. It is a 0.84. So 0.84 will be specific volume. 4.1, I have to do some iterations. So here it is given as 0.88, and this is a 0.8687. So I will write it as a 0.877. Okay, so it is little bit less than 0.88. So I have taken 0.88, sorry, 877. Okay, so this is 0.877 and this is 0.84. So find out these values, mass flow rates. So calculate mass flow rates and tell me the value. And remember the unit. So this 300 is meter cube per minute. And this specific volume, obviously it will be meter cube per kg. Okay, so this meter cube will cancel. Whatever value you will get, that will be in kilogram per minute. And this value will be also kilogram per minute. Okay, so tell me the values quickly. So I have one answer. Others also please confirm that answer. Pradyumna, are you there? So confirm that answer. Sonali, Pradeep, to calculate and confirm your answers. So do take active participation. Calculate the values. This way, your brain will work. Okay. Simply, if you are seeing the lectures and observing the screen, you'll you'll not get the hands-on experience. Okay, so I'll take that value M1 as Rohit has calculated 342, and M2 has calculated 952.38, and this is 0.075. Okay, so I'll put these values in this expression. So this will come to like 342.075 divided by is equal to, now H3 is unknown, so I will leave as it is. H3 minus H2. H2 here we have calculated as 30, so this will be minus 30 divided by H1 we have calculated here as a 65. Okay, so that I will take 65 minus H3. So solve this expression and see what you get the value of H3. Okay, so you don't need to go solve this in steps. Simply if you put this expression in your calculator and if you go for solving, it will directly give you the value of H3. So H3 will be kilojoule per kg of dry air. So calculate the value of H3. You can do this equation in steps also, or otherwise you can put this equation directly into your CAD-C, and if you go for solving, it will give you the value of H3. So calculate the value of H3. Okay, so I have one answer here, 39.25. 39.25. So if you solve this equation, you'll get a value 39.25. Okay, now I'll show you how to plot the point H3 or the point 3 here. So you have a chart already here. Okay, so point P1 was 30 and 50 here. So this was the point P1. Point 2 was 22 and 10 degree Celsius WBT. So this is our point 2. Point 2 here. I have to join with the help of a line. That line should be a straight line. Okay. Then Rohit has calculated that value as 39.25. So on this scale of enthalpy here, I have to locate enthalpy value of 39.25. So here it is 30, this will be 32, 34, 36, 38. So here it is 39. So it will be like nearer to 40. So I have to follow this line here, and when this line will intersect our adiabatic mixing line, then I have to stop there. So somewhere here I'll get a point 3. Okay, so this will be my point 3. If I look for the WBT point here, I'll get a temperature of this. So this is a temperature I'll get. This is nothing but 21, 22, 23, 24. If I go in horizontal direction like this, I will get a specific humidity here. Okay, this is given as 6. So 6 grams per kg. I'll get a specific humidity in this case. If I go in inclined direction, I will get a WBT point. So if I go in inclined line here, so this is less than 15, let us say 14. So I will get a 14 WBT. Okay. What else they have asked us? Dew point temperature. So for finding the dew point temperature, I have to go this backward direction in horizontal way. So here I will get a value. So this is the value. here, and this is somewhat greater than 6, and this is a 6.5. Okay, so this is how I'm calculating. I have plotted a point 3. If I go in vertical direction, I'll get a WBT of 24. If I go in horizontal direction, here I'll get a specific humidity of 6. If I go in inclined direction, I'll get a WBT of 14. If I go in horizontal direction in backward way, so I will get a dew point temperature of 6.5. Okay, so with practice you will get hands on it. Okay, so I think that data is gone somewhere. Yes, it is here. So from chart, I can say point 3. At point 3, enthalpy is 39.25, which is already calculated. But dew point temperature is 24 degrees Celsius. WPT temperature is 14 degrees Celsius. Specific humidity, W3 is nothing, but here 6 grams per kg. And dew point temperature, as we have calculated, how much it was? Okay, so that was something nearer to 5 degrees Celsius. Okay, sorry, that was not 5, it was related to 13 degrees Celsius. Okay, so these are all your answers. I will repeat this process once again from the beginning. So we have a problem here of adiabatic mixing. We have one stream which is at 22 degrees Celsius dry bulb temperature and 10 degrees Celsius dew point temperature. Another stream is at 30 degrees Celsius dry bulb temperature and 50% RH. Then we have adiabatic mixing and we have to find out its final values. So I have plotted point 1 here, then I have plotted point 2 here, and I have drawn a line. Somewhere on the that line, that point 3 will lie. Okay, how to find out that? So we have already derived this formula here, and we have to just put the values there. So H3 was unknown there. I have calculated H3. Now on the psychrometric chart, I have first found out this value 39.25. Then I followed the constant enthalpy lines, which are the inclined one. Then I follow this line. Whenever this line intersected this another line, adiabatic mixing line, there I have said that this is my point 3. At that point, I have calculated other values. If I go in downward direction vertically, I will get a dry bulb temperature. If I go in horizontal direction, I will get a specific humidity. If I go in horizontal direction in the back, I will get dew point temperature. And if I follow this inclined line, here I will get a wet bulb temperature. Okay, so this is how you read the psychrometric chart and solve the numericals. Okay, so I hope the concept about adiabatic mixing I have cleared. I have taken one example, and tomorrow on our timetable, my lecture is not there, but still I will try to take, because there will be a huge gap between this Diwali vacations. So tomorrow also I will take another numerical related to adiabatic mixing, and also one more numerical related to heating and humidification, drying processes, that will also I will take. Okay, so we'll solve more numericals tomorrow, so don't miss that lecture also, right? And once again I will tell, Diwali vacations are from 13 to 17. From 19 to 21 your ISC will be there. RAC paper will be on 21st November. Okay, so if you have any questions you can ask. Meanwhile I will take the attendance.